Hello everyone, I'm George Orlando and today we'll be discussing the key findings from the paper titled Barrier Lyapunov Function and Model Reference Adaptive Control on Native Spaces. Before delving into the details of the work, let's refresh some results in classical MRAC. If no unmatched disturbances are present, classical MRAC allows the closed-loop trajectory to asymptotically follow a desired reference trajectory despite parametric finite-dimensional uncertainties. Sources of such uncertainties lie in the state matrix A, the control uncertainty matrix lambda, and the parameter matrix theta. Such constant quantities can be totally obscure to the controller. However, one of the biggest limits of parametric MRAC is that the nonlinearities must be in regressor form, where the parameters are uncertain, but the functional shape phi is completely known. Classical results can be extended to a broader class of nonlinear uncertainties. Similar guarantees can be obtained if the functional shape of the matched uncertainties is unknown but assumed to live in a reproducing kernel Hilbert space. In this case, thanks to the reproducing property, we know that the nonlinear function can be written as an infinite linear combination of kernel functions. Similarly to classical MRAC, recent works have shown that in the absence of unmatched disturbances, the control law with adaptive laws shown on this slide can force the tracking error of the closed-loop system to zero despite infinite dimensional uncertainties. However, this controller is not realizable in practice since the last term in the control law comes from the solution of a partial differential equation. To make it practically implementable, an orthogonal projection operator must be adopted to project the infinite dimensional uncertainty onto a finite dimensional approximation space denoted as H sub n. Practically speaking, we approximate the infinite linear combination by means of a finite combination of n basis functions located at n centers in the state space. The approximation error will cause an unmatched disturbance term d of t to appear in the plant model. Therefore, in the finite-dimensional approximation, we must employ robust adaptive laws that, parallelly in classical MRAC, ensure boundedness of all the closed-loop signals and convergence of the tracking error to a set around the origin whose size is dependent on the goodness of the function approximation. Notably, the PDE has now been turned into a set of ordinary differential equations. In this formulation, there are several problems. First of all, kernel centers are placed a priori in the state space, and having no guarantees on the tracking error means that we either have to cover large regions of the state space with kernel centers, thus increasing n, or we take the risk of having regions with low kernel density and therefore low quality approximation. Moreover, no works on non-parametric MRAC have included uncertainties in the matrix lambda thus far. In this work, barrier functions are employed for the first time in MRAC on native spaces to impose hard constraints on the tracking error. This framework allows the user to concentrate kernel centers in the constraint set only in which the tracking error is guaranteed to lie at all times. Moreover, equivalence of the RKHS's H and HL was proven, allowing for a broader class of uncertain plant models to be treated within the novel infinite dimensional framework for adaptive control. Here is an example of how imposing a constraint set on the tracking error, represented by the black dashed lines, allows the user to place kernel centers in smaller proper subsets of the state space. Such hard constraints on the tracking error are imposed by the user through the definition of a constraint function h. Such function can be either constant or time-varying, and in the latter case, the constraint set can be tightened or relaxed based on some user-defined criteria. Once again, the constraint function h can be varied by means of a user-defined adaptive law. However, if the variation over time is too aggressive, then h user is approximated by integrating a saturated adaptive law. Such upper bound on the adaptive law makes sure that the energy injected into the system by the contraction of the constraint set does not cause the total energy to grow. Moreover, we cannot ask the constraint set to shrink beyond a certain threshold denoted as omega that is determined by the upper bound on the unmatched disturbances. Here we see an example of the tracking error trajectory that is confined within the constraint set at all times. The constraint set can shrink up to the ball of radius omega, which is the set in which the unmatched disturbances dominate. Finally, here is the modified finite-dimensional control law that confines the error into a user-defined constraint set at all times. The constraint function h manifests an explicit dependence on time. And for the time-invariant constraint set, it is enough to drop such time dependence. However, if all the terms involving the constraint function h are deleted, then we get exactly the unconstrained RKHS case. Finally, we show some simulation results for a two-dimensional case. Here, hard constraints are imposed on the tracking error, whereas the adaptive law for the constraint function is defined so as to impose soft constraints on the control effort. Again, this is how the kernels were placed in the state space for this simple case study. First, we compare the unconstrained case against the time-invariant constraint set. The left image shows a constraint trajectory. The right one shows the unconstrained case. The counter indicates how many times the unconstrained trajectory escapes the constraint set, therefore approaching regions with poor approximation capability. At 30 seconds, an actuator deterioration is simulated by changing the entries of the lambda matrix. The tracking error time history clearly shows the superiority of constrained RKHS with respect to the classical case. This switch in green indicates the time at which the lambda entries are varied. One of the most interesting features of the proposed adaptive law is that the plant is guaranteed to behave according to user-defined performance criteria at all times and not just ultimately. This is the L1 norm of the tracking error, which just confirms the results previously shown. In this simulation, there is a small price to pay in terms of control effort, even though the curves for the unconstrained RKHS and the time-invariant constrained RKHS are still quite comparable. Next, we compare the time-varying constraint set against the time-invariant case. The left image shows a time-invariant constraint set. On the right, we see a time-varying one. It is apparent that the constraint set changing over time, and whenever extra control authority is available, the constraint set shrinks. On the other hand, if saturation limits are approached, then the constraints are relaxed. At t equal to 30 seconds, when actuator deterioration takes place, the time-varying framework shows less sensitivity to control efficiency changes as the trajectory displays fewer oscillations. Here, the tracking errors are compared. The time-varying case shows increased flexibility in terms of user-defined criteria. From 0 to 30 seconds, we see how, in the transient phase, the constraint set diameter grows whenever the control magnitude approaches saturation bound, and tightens whenever extra control is available. The L1 norm on the tracking error shows overall superiority of the time-varying case in terms of tracking error, with, remarkably, also superior performances in terms of control effort. This is the end for today. Thank you for watching. For further clarification on theoretical findings, please consult the original paper. Moreover, all codes are available at this link, which you can also find in the video description. For any questions, please email Dr. Laflido at this email address. Finally, we would like to thank NSF and PNRR for funding this project. Thank you again for watching.